Hello friends, we are continuing with the series of videos on cuda. So today's video is going to be on a small GPU Jetson Nano and a small program addition of two variables using cuda. Now as you can see on the screen, this is a simple addition using cuda on Jetson Nano. So what is cuda? In every video we are explaining cuda is a parallel computing platform and an API model that was developed by NVIDIA. Using cuda you can utilize the power of NVIDIA GPUs and you can do cuda programming on this. Now the simple addition code, actually that is what almost everybody is interested, like I want to add A plus B is equal to C. So that is what we are trying to do here. So from the past videos, you know that actually stdio.h library required, cuda.h library is required. Here the global function, not exactly, it's also called a global function. Yes, it is the GPU kernel function, that is add num. Then A, B, C pointers are being passed. You are basically adding, and you are saying C is equal to A plus B, but they are added through pointers. That is the only difference. Now here the important thing is normal function is return C. Here you need not return any C. That is the beauty. Because the kernel, when you do the cuda level programming, you don't have to return C. Indirectly it gets returned through a function which we will be explaining soon. So now the main program looks like that. Integer A comma B comma C, they are a simple variable. You are creating a pointer to each D underscore A, D underscore B, D underscore C. That is the pointers to ABC. Then in size of an integer is a constant. It is whatever, actually it is 4 or something, may return. Now cuda malloc pointer to pointer, that means you are pointing to a device. That is what is a pointer to pointer, not in this particular CPU, but is far off place, that is star star. Then you are allocating a space for A, allocating a space for B, allocating a space for C at the device, far off at the GPU. Now you are initializing A is equal to 2, B is equal to 7 in the local CPU. Now you do a copy from mem copy into the A. The content of A is being passed into the GPU or into the device. Then you say cuda mem copy host to device. When you say this, actually the A is being transferred into that. Same way we are transferring B, and after that you are launching a kernel, add kernel, that is on the GPU, add num. This means one block and one thread, because we are doing only one calculation. Why do you want to run it on multiple threads? You are passing the pointers, not any data, pointers to A, pointer to B, pointer to C. Now this is the memory address of each data where it is sitting in the remote location. When you say, after doing this, you get the result. So there is no return of C, but it will get returned through this command mem copy C into the C variable. It gets returned into the CPU from the remote device pointer C. Then you say cuda mem copy device to host. From device to host it comes back. Then you are just deleting all the pointers to avoid segmentation fault, etc. So that you are cleaning up the memories to avoid any memory leakage. So finally the result is being printed. The same thing when I typed it on a nano compiler, it looked like that. It is exactly same program. Number of threads is set to 1. That is the only thing you can see. Now you can also do like I explained in the previous videos. Once you create nvcc -o op program2.cu, That means you can do a NV profile of that. You want to see how much time it took in the GPU to do this. It took 20.6 microseconds. Remember, when you wanted to print only one printf command, actually one hello, print hello, it was taking around 700 microseconds. And when we ran it on a 3 thread also, it was taking almost same time. Now, whenever this calculation thing is coming up and GPU is more interested, it is taking only 20 microseconds. That is the beauty of this. And if you run the same thing on 256 threads, why do you have to run at all? No, you have only one calculation to be done. You have to add 2 plus 7 is equal to 9. But there is no need of allocating so much of threads actually. But still, if you do it also, it will only utilize only one thread and remaining will be left unused. So the same kind of programming, you can see that actually exactly same except the threads have been changed in the kernel launch. See, when I did 256, you can see it is taking now 22 microsecond, and initial case it was 22 microsecond. Then it took here 18.5 microsecond. So here the integer value, remember it was 9, so 2, we were adding 7 plus 2, we were getting 9. And so what we were trying to say is, in this particular case, actually when we are using more number of kernels or less number of kernels, it is almost taking the same time, around 20 microsecond. And this is for thread profile for 1,1, this for 1, because the remaining is unused. Now we will come into the demonstration of this. We will practically show you how this has been done. The file name has been, so we can open this file, nano simple addition using cuda. So this is the program, and you can see that actually this is exactly same program, adding 2 plus 7 through GPU. So you can come out of this program, and I am just compiling this program NVCC simple addition. It will create a dot out. So you can run /a dot out to see the output. It is printing 9. I added 2 plus 7 correctly. Then if I do the profile, this is how it looks like. So this was taking around 18-20 microseconds. Remember, actually, let us see that practically whether, see, it is taking 20 microseconds. This is what is the most important thing to be done. Remember, and in detail analysis also you can do actually. That is, see that CUDA memory copy, how much time it takes, host to device, device to host, how much time it takes. All very fast, it's happening in microsecond. And add num function, it takes the kernel time is around 20.7 microseconds. So I would probably add all these 3 to get almost 27 plus 6, that's 33 microsecond almost for the things to be done in the GPU. Thank you.